polarization of light. Light is an electromagnetic wave in which the time-varying electric field, vector E, sometimes called the light vector, and magnetic field, vector B, are mutually perpendicular to each other, and also perpendicular to the direction of the propagation of light wave. The phenomenon in which the light electric vector variations or vibrations are confined to a particular direction in a plane is called polarization.
First controllable atom SQUID, November 02, 2012. Facebook, LinkedIn, Twitter. Researcher Kevin Wright checks part of the experimental apparatus. Credit: NIST scientists have created the first controllable atomic circuit that functions analogously to a superconducting quantum interference device, SQUID, and allows operators to select a particular quantum state of the system at will. By manipulating atoms in a superfluid ring thinner than a human hair, the investigators were able for the first time to measure rotation-induced discrete quantized changes in the atom's state, thereby providing a proof of principle design for an atomtronic inertial sensor.
Polarization. In the year 1865, Maxwell proposed electromagnetic wave theory. According to this theory, light is an electromagnetic wave. It consists of vibrations of electric field and magnetic field in a direction perpendicular to the direction of propagation. Also, the vibrations of electric field and magnetic fields are confined to two different planes that are mutually perpendicular to each other. It was proved that electric field vibrations are responsible for the vision. Therefore, vibration of light means electric field vibrations.
Optical vortex. Read in another language. Watch edit. Diagram of different modes, 4 of which are optical vortices. Columns show the helical structures, phase front and intensity of the beams in optical vortex, also known as a photonic quantum vortex. Screw dislocation or phase singularity is a zero of an optical field, a point of zero intensity. The term is also used to describe a beam of light that has such a zero in it. The study of these phenomena is known as singular optics.
If we neglect the vibrations of magnetic field, the representation becomes simpler. Now, the electromagnetic wave will look like a pure transverse wave. Every vibrations will have a particular plane of oscillation. The oscillation can be in this direction, and even in this direction. We know that electromagnetic waves are produced by excited atoms. A particular atom may produce electric field vibrations in this direction. Its neighbor may produce vibrations in this direction. Similarly, different atoms of a material can produce vibrations in a variety of directions. Due to this, a common source of light like incandescent bulb, candle flame, fluorescent lamp, etc. emit light that have electric field vibrations in a number of directions. This type of light beam, which has vibrations in more than one plane, is called unpolarized light. Similarly, a light beam which has vibrations in only one plane is called polarized light.
In the nascent but fast-moving field of atomtronics, flows of atoms are used in ways analogous to the flow of electrons in conventional electronic systems. It could be argued, says team leader Gretchen Campbell of PML's Quantum Measurement Division, that this is a true atomtronics device where we have a controllable circuit element. SQUIDs work because of the fundamental property of superconductors. When exposed to an applied magnetic field, a ring of superconductor generates currents which produce magnetic flux exactly cancelling the external field. When the current reaches a critical value determined by a junction or weak link in the ring, it jumps by a discrete amount, allowing a quantized amount of flux to penetrate the ring. Measuring the effect of that action on the current across a junction allows one to measure the strength of the applied field, and squids are routinely employed to detect very weak fields such as those produced by brain waves or nerve impulses in muscle tissue.
Explanation edit. In an optical vortex, light is twisted like a corkscrew around its axis of travel. Because of the twisting, the light waves at the axis itself cancel each other out. When projected onto a flat surface, an optical vortex looks like a ring of light, with a dark hole in the center. This corkscrew of light, with darkness at the center, is called an optical vortex. The vortex is given a number, called the topological charge, according to how many twists the light does in one wavelength. The number is always an integer, and can be positive or negative, depending on the direction of the twist. The higher the number of the twist, the faster the light is spinning around the axis.
Polarization by reflection. The simplest method to produce plain polarized light is by reflection. This method was first discovered by Malus in the year 1808. It was found that when an unpolarized light is incident on a surface of transparent medium like water or glass, some part of the light got reflected and the rest got refracted through the material. Here, the straight arrows represent vibrations perpendicular to the plane of the surface, and the dots represent vibrations parallel to the surface. Now, if we observe the reflected light, we can see that it contains more number of dots than the arrows, which means that the reflected ray is partially polarized. Similarly, if we look at the refracted ray, we can see that it is almost unpolarized.
Campbell and colleagues in the laser cooling and trapping group have long been investigating analogous behavior in toroidal Bose-Einstein condensates, BECTs, ultra-cold, donut-shaped ensembles of atoms that are all in the same quantum state and form a superfluid. To create rotation, which is the superfluid counterpart to external magnetic fields in a squid, the team introduces a green laser beam perpendicular to and penetrating the plane of the superfluid ring, and slowly rotates the beam around the ring. See animation.
Polarization by scattering. Just as unpolarized light can be partially polarized by reflection, it can also be polarized by scattering. This is also known as Rayleigh scattering. Since light waves are electromagnetic in nature, they will vibrate the electrons of air molecules perpendicular to the direction in which they are traveling. The electrons then produce radiation that is polarized perpendicular to the direction of the ray.
This spinning carries orbital angular momentum with the wave train, and will induce torque on an electric dipole. Orbital angular momentum is distinct from the more commonly encountered spin angular momentum, which produces circular polarization. 1. Orbital angular momentum of light can be observed in the orbiting motion of trapped particles. Interfering an optical vortex with a plane wave of light reveals the spiral phase as concentric spirals. The number of arms in the spiral equals the topological charge. Optical vortices are studied by creating them in the lab in various ways. They can be generated directly in a laser. 2, 3 or a laser beam can be twisted into vortex using any of several methods, such as computer-generated holograms, spiral phase delay structures, or by refringent vortices in materials.
Consider that you are sitting at this point in this room, and a music system kept in another room is playing music. Since the door of this room is open, you are able to hear the music even if you are not present in front of the door. This means that sound waves somehow bent across the door and reached your ears. This phenomenon of bending of wave around the corners of an obstacle or aperture is called diffraction of a wave.
The beam acts as a sort of optical paddle, causing the superfluid Beck atoms to rotate. Just as a superconducting ring admits flux when the current exceeds a critical value, the ring of superfluid admits a vortex, resulting in a change in the circulation of atoms around the ring. Like everything else in the quantum world, the properties of those vortices are quantized, that is, they occur only at discrete values, and led to quantized circulation states in the Beck. Campbell's team was able to observe and measure those quantum increments and for the first time was able to control the onset of discrete circulation states by tuning the power and rotational speed of the green laser.
At it. An optical singularity is a zero of an optical field. The phase in the field circulates around these points of zero intensity, giving rise to the name vortex. Vortices are points in 2D fields and lines in 3D fields, as they have codimension 2. Integrating the phase of the field around a path and closing a vortex yields an integer multiple of
VOP.
This integer is known as the topological charge, or strength, of the vortex. A hypergeometric Gaussian mode, HIG, has an optical vortex in its center, the beam, which has a form
Psi.
EIM. E, R2, is a solution to the Piraxel wave equation, see Piraxel approximation, and the Fourier optics article for the actual equation, consisting of the Bessel function. Photons in a hypergeometric Gaussian beam have an orbital angular momentum of mh with stroke. The integer m also gives the strength of the vortex at the beam's center. Spin angular momentum of circularly polarized light can be converted into orbital angular momentum. 4. Creation edit. Several methods exist to create hypergeometric Gaussian modes, including with a spiral phase plate, computer-generated holograms, mode conversion, a Q-plate, or a spatial light modulator. Static spiral phase plates, SPPs, are spiral-shaped pieces of crystal or plastic that are engineered specifically to the desired topological charge and incident wavelength. They are efficient, yet expensive. Adjustable SPPs can be made by moving a wedge between two sides of a cracked piece of plastic. Computer-generated holograms, CGHs, are the calculated interferogram between a plane wave and a Laguerre Gaussian beam which is transferred to film. The CGH resembles a common raunchy linear diffraction grating, save a fork dislocation. An incident laser beam creates a diffraction pattern with vortices whose topological charge increases with diffraction order. The zero order is Gaussian, and the vortices have opposite helicity on either side of this undiffracted beam. The number of prongs in the CGH fork is directly related to the topological charge of the first diffraction order vortex. The CGH can be blazed to direct more intensity into the first order. Bleaching transforms it from an intensity grating to a phase grating, which increases efficiency. Vortices